turn our focus to the cutting edge of connectivity, intelligence, and immersive experiences, exploring how XR will evolve in the 6G era. It is my privilege to invite Dr. Kaushik Dey, Head of AI Research at Ericsson India and the leader of the 6G of India Research Program, to present XR in a 6G world. With over 2 decades of experience at Ericsson and IBM, Dr. Dey has driven pioneering research in AI, zero-touch networks, adaptive multi-agent systems, and ultra-low energy AI. His work spans reinforcement learning, autonomous agents, and real-time agentic frameworks with more than 25 international patents to his credit. May I now request Dr. Kaushik Dey to please take the stage and lead the session.
Good morning, and thank you. It is an honor to be here and to present it before this wonderful audience. So we had some brilliant session earlier about the AR/VR devices. We saw that what some of the AR/VR devices from Meta can do. Now it will be immensely useful if we are able to transmit such experience across hundreds of kilometers or even across countries, because locally you can only do as much. So the question comes, do we have the necessary technology right now in order to scale such experience, in order to transmit at scale across countries, across continents, such that that entire human perspective, which my earlier colleague was pointing out, that can that human perspective be extended beyond the borders? Turns out that we are heading there, but we may not be completely there. In a sense that in some experimental settings, it is still possible to transmit an XR kind of experience, at least in some parts. So say, for example, we have a collaboration project with Volvo, currently in India, where what we are doing basically, there is a factory, remote factory, and then there is an office, a city office. So using XR, we are enabling such that the worker in the factory floor can collaborate with another technical person sitting right in the city office, so that they can work together in order to maybe assemble a truck or to solve certain problems together, collaboratively. Now this process, it has immense significance for a country like India because we are so diverse. There are, we are so scattered across geographies, and why only India? Even for Global South, the theme being Global South. But this seemingly very interesting experience, of transmitting or able to control a truck manufacturing or a truck repair from hundreds of kilometers away is actually fraught with challenges. What it needs is an extreme low latency, a latency of the order of 20 to 30 milliseconds. Now, that is a tough call given the way the networks are dimensioned today. So here in this experimental setting with Volvo, what we are doing, we are customizing the network such that we can achieve a kind of a 20 millisecond latency. But can we do it at scale? Can anybody do it like this across cities, across the world? Well, the answer is not yet. And that is where we are moving when we call the 6G world. However, to implement this in future networks like 6G, it will take different technologies also. The technologies which we use today for transmissions, which are still, it follows Shannon theory, it may not be sufficient to get us there. And that gets us to, the Weber's theory, that it is not enough to only transmit information accurately. Today we can do it by OFDM and other principles. But it is also important to understand the meaning and the context of what you are transmitting. But how does that understanding the context of what you are transmitting help you in achieving multitudes, let's say magnitudes of advantage when you transmit information? So we will look at that. So when we look at the previous generation of communication, still 5G, it was mostly about, first it was about the throughput, the amount of information you can transmit, and then 5G brought in the latency. In the 6G, we are not talking just about the characteristics. What we are talking about the experience, the merging of the digital and the physical world. In a sense, the cyber-physical interaction. The cyber-physical world, as we say, which would be also aided by all the different, the AR, VR glasses and the things that we saw. So in a sense, when we talk about this digital reality and blending it with the physical reality, what happens is that new evolved use cases will come. It will be like if we are operating on the digital world, if you are operating on the virtual world, it will look like seamless. It will look like seamless experience as if you are operating on the virtual physical world. There are various tools and techniques which will aid it, but let's see a short video on how it will look like. This should play. So here we saw a couple of scenarios. Say for first the bicycle approaching the intersection, and as the bus approaches, there is a sensor which senses both the vehicles traveling in the collision course. And then there is an actuation which is automatically induced. The way it can be done is if we are able to create the digital reality, a continuous digital reality of the physical world, then we can actually program around it using all the AI techniques that we have. We can predict its heading for the collision course. And then on a very minimal latency, we can induce that actuation either in the bus or in the bicycle. Similarly, you saw two people kind of look like two people, but actually one is real, another is virtual, who are sitting across the table and having a lunch. But then what it calls for is not just transmitting the image, the video of the person, but also transmitting all the different senses, the sense of touch, smell, and all of that. So there are these different use cases which should be possible. But then comes the question is what it entails. In order to realize such use case, what we need to send tons of information across all the 5 senses. We need to send it in a low latency mode, and we need to send it in a very high throughput. Now, if we go from 5G to 4G to 5G, or say, from 4G to 5G, there was kind of orders of magnitude gain that we found in terms of the amount of information that we can send. But when we go to 5G to 6G, probably the uptake is not so much. It could be about, say, twice the gain that we have in terms of throughput. But will it be enough to achieve these kind of use cases only? The answer is no. So what are the different technologies that we are looking at? I'll give you a glimpse of one such technology which we are looking at, and of course this might not be all. So one of them is a semantic information transmission, or what we call as a semantic communication. The entire idea of semantic communication is that we don't directly transfer the data. we transfer the meaning of the data, we transfer the context, and we transfer certain signatures. Using those signatures, we then again regenerate the data at the receiver's end. And thereby what you have when you are transmitting, you are only transmitting certain signatures, which are many, many times less as compared to the total volume of information which you were sending. So say, for example, using this picture, what we see is we are transporting an image or a video of a girl dancing. Now, the background does not change so often. Probably it could change only in a second or a mill, or say for 5 seconds or so. So all we need to transport is actually the image of the girl, how the image of the girl changes. And then when you go even deeper into it, maybe at a millisecond level, we do not need to transmit the face and everything. We can transmit the face maybe at 500 millisecond interval or so. But the hands we can transmit maybe at 100 millisecond interval, the position of the hands and not the image of the hand. So using that, we can achieve the kind of efficiency which is unimaginable in today's transmission. And then this concept of semantic communication is applied or is applicable across many areas, starting from holographic communication, in terms of even drone communication, in terms of any activity detection from remote, or any other things, or most of the use cases which you saw in the previous presentation. Now, let's look at the schematic process of semantic communication, or what are the steps that we need to do in order to pass the semantics accurately and then again accurately decode it at the receiver end. The first thing is the semantic extraction. We need to understand the context. And remember, the context changes, right? So what you are seeing now, it might change the next moment, the environment might change. Let's leave aside those complexities. We first need to extract the context. And then we need to, from that context, we need to filter the right information. We need to generate the signatures. And then we need to encode it and send it over for the transmission. At the receiving end, we need to decode it and we need to infer it before passing the information. So this is, of course, a much simplistic picture, but overall, if you look at the moving parts, overall, if you look at what are the principal components, it's pretty much the same. Now, I will probably take some liberty to show go a little bit deeper into the technical parts of it. So some of the research papers of how they have implemented it. So this is a relatively, I would say, a simpler use case where all we are transmitting is image and data. So what we can do, first we can do, we can use any of the convolutional networks, we can resize it, and then we get kind of a signature of the image. And then the further convolutional layers can actually decode it and move it from the real to the complex domain such that it can be transmitted. At the receiving end, we first have to decode it, and once we decode it, there is a process which merges the image and the text data in terms of context, and then you get the information. Of course, it's probably more involved than what I am talking about, but more or less that is the general idea. Having said that, how does the overall performance look like? Because ultimately, this will be popular only if you are able to regenerate it in a lifelike image. So if you look at the curves, there are a couple of lines, but I will draw your attention only to this black curve. In this simplistic scenario of image and text, you will see the black curve is kind of quite close to this dotted line, which is the error-free transmission. So we are doing pretty well when it looks at image to data. Now again, these are some laboratory conditions So when it has been transported, these experiments have been more simulated. So the noise which you get when you transmit a data from one end to another, it has been induced here through some white noise. But the reality in real world, it might be more complex. But let's look at a slightly more complex scenario which is close to today's discussion, which is about holographic communication. So here the approach, one of the approaches which is taken is, we take pictures, all these x1 to xn is the pictures taken at different angle of the subject. And then that is encoded using an encoder. And these encoders are a series of convolutional layers. And from that encoder, we then, one of the steps it's not showing here for simplicity is there is the further encoding into the channel model so that it can be transferred into the channel. So we introduce some white noise and then we further do the channel encoding. It is then transported across the wireless channel, or it's rather simulated. The transfer across the wireless channel is simulated. And then the first it is decoded. But then after the decoding, there are a couple of important steps here. You are getting multiple images at a certain point of time of the same subject. So there are a lot of redundancies. And those redundancies are good, because from those redundancies, it helps us to reconstruct more or less a realistic video of that particular, using the images. And the way it is done is, they take kind of an average feature, the average of all images, and then there are some techniques which are done using transformers. We will not get into it, in order to figure out the similarity between the current image and the averaged features using self-attention. And then there is a volume renderer which is more about the tone of the particular video, and finally it is rendered. So it gives decently good images. It gives decently good results. Now this is more details, we will not get into it. But then there are two aspects which we will get finally at the last part of this presentation. One is, how do you measure the goodness of such semantic communication, and what are the challenges? So when we talk about the metrics part, one of them is latency, the inference latency. If we have to infer it at your device side, today your device does not have a GPU. It does not have a processing unit capable of running a decoder, a fairly, like a decoder having if not a million, at least 500,000 parameters. And then even if we have that GPU, the first question is, what is the inference latency? Any LLM, say it takes about 1 second or so. With reasoning, it will take more. And if you are able to use smaller models, it will still take about 500 milliseconds. But then the latency, what we are trying to get at for these kind of application is about 50 to 100 milliseconds. So how do we get to that part of the latency? It calls for an evolution in both the hardware and the algorithms. Then the energy efficiency. The moment we have compute in your device, say for an iPhone, which today lasts for about a day, it will only last for about 28 minutes in many of our experiments. And that's not feasible. So how do you use chips which are energy efficient and are still able to decode at a acceptable latency? Of course, the security, and then comes the robustness and the adaptability. When you are transferring over the experimental environment, it's fine. You're introducing the white noise and you are then decoding. But when you take it to the real world, your environment changes. The radio environment, it changes every 10 minutes. So as it changes, the dynamics of the environment changes. And as the dynamics changes, the model which you have trained using the training data is no longer capable of doing the right inference across the new environment because the characteristics have changed. So how do you generalize such a model? How do you generalize such an inference? So that's also a measure to which all this semantic communication model have to stand up to. Then some of the challenges. One of the challenges, the real world challenges is with respect to operational complexity. The operational complexity today, it means that we have different network OEMs. You can take, say, Ericsson, Nokia, Huawei, Samsung. And then you have these different, the cell phone providers, right? Tens of them. Across the world could be 100 or more. So now when you have an encoder and decoder, every time you encode and decode, OEM has a proprietary model, and that particular cell phone also needs to have all those proprietary models across the vendors. So this introduces logistical challenges. How many models can you house? And how can you do that model management? And this is one of the key bottlenecks when we are discussing in the next 6G release of Release 20, which is started, that how do we manage such model, how do we do such model management? Task adaptability, we talk about. Model updates, another related challenge, and that is also related to the model management part. Inference time, we talked about that. The current inference time at edge clearly exceeds the acceptable timeline, and that calls for an improvement both in terms of the model and also in terms of hardware. Like we did some recent experiments where that 3 seconds, some of the reasoning models which was taking 3 seconds, it could be brought down to 300 milliseconds under lab conditions. But again, it is still under lab conditions. This is still, under a lot of constraints. And finally, the compute. Today, inference at the edge doesn't exist. It doesn't even exist at the base stations, leave the cell phones. So we need a totally new kind of hardware. We need new hardware designs in order to get there such that the inference can happen at the edge. The encoding, if you need to do it, can happen, the decoding, if you need to do, it can happen either in the cell phones or at the edge. So these are all the challenges, but these challenges does not prevent us from moving ahead. The good thing is, there are multiple research work in semantic communication for XR/VR going on. Currently, we are starting one of the big projects, one of the big collaboration projects with IIT Madras. And if you'd like to be a part of it, please let us know. We think in another 2 years, we will be able to probably get the first prototype out, and then probably it will take another 5 years for a full-blown adoption of such use cases. With that, I come to the end of my presentation. Thank you for the opportunity, and if there are any questions, I'll be happy to take. Thank you. Yeah, please. Sorry. I'm sorry. Right. Yeah, so again, that is something under experimental conditions. As of now, okay, we have started in 2 parts. One is how you can transmit, the action which is taken, say 100 kilometers away from the factory, how that action can be pushed right at a latency of, say, 20 milliseconds or 30 milliseconds, and that can be actuated in the truck. So that's one part of it. The second part of it, when you are dealing with the entire, the truck assembly or the repair of it, not every part, and this is the research part, not every part of the truck needs to be transmitted. So how do you semantically identify which are the moving parts? and then only transmit that part, and then you kind of, regenerate the entire image in the city office such that the person in the city office, he can be in sync with whoever is working in the factory, and the actuation can be taken in the real time. So that's the semantic part of it.
It's under development, right?
It is under development. Of course, it is under, I would say one part is under research, another part is under development. It's more about a configuration. We will get to that in 5G definitely, but the research part, it will take some time to mature.
Nice presentation.
Thank you. Any other? Sorry if I can't see a hand, please speak up. Okay. Yeah, please.
Hello, I'm Swati.
Hi.
So I'm an experienced designer, and I was intrigued when you said about the Volvo and Ericsson research that was happening. We actually, for one other client, had delivered something very similar, where there is a user who is, or a field service engineer in a different part of the world, and there is a remote service engineer who's like a senior on the other part. And he's not able to communicate efficiently, and that's why we used VR and XR, like kind of MR and VR there to actually help them coordinate at the same time. But what we found as a challenge was the person on the other end, like the RSC, is not able to see whatever is there in front of the FSC for a seamless communication. Do you think these semantic research that you're carrying out will actually ease in this out? Because this is a problem that we realized very recently. So thought I should just bring up this question.
Excellent question. Is Rohit in the room somewhere? Okay, but that's fine. So so Rohit is a PhD scholar who works with Professor Manivannan. And I gave his example, like I will get to that. But then the short answer is, of course, yes. And what you refer to as is the efficient communication, the efficient video-based communication. That is possible even today. Using, of course, it could need some configuration at the network level if you have to transfer that image at a very low latency, if you have to transfer the video at a low latency, but that is possible. The bigger challenge comes when you have to transfer the actuation at the low latency. Here, the example which you said, the field service engineer was at the field and the remote engineer was remote. So it was just a matter of looking at a real-time video and advising him. Now imagine if both of them are working together on a machine, and then both the actuations need to reach at the same time, right? Otherwise, the person in the field, they will be doing an action, and that action would be perceptible, say, 100 milliseconds later, and then he would perceive the wrong environment state when he takes the action. So that's where semantic communication would be very useful, because we will not be transferring the entire information. We will only be transferring the signatures. I give this example, and that's why I was looking for Rohit. So Rohit, we did an experimental project with Professor Manivannan, where we built a device which is called the Stetho ECG. And you can see it in his lab also. It's a device like a small, like the size of the palm, which can record the heart sounds as well as the ECG. So instead of having a 12-lead ECG, you can have a small device. You can, connect it using your using your cell phone. You can do a hotspot. And it can, in real time, it can send the heart sounds as well as the ECG data to a doctor who is hundreds of kilometers away. We showed this in IMC, whereby the patient was in the IMC hall and the doctor was in AIIMS, or he was in Ramachandra Medical Institute in Chennai. Now, here a funny thing happened. The first day in IMC, Indian Mobile Congress, as it suggests, everybody was showing their applications in mobile. The entire thing, the entire network kind of got clogged up. So you could not even surf the net. You could not even see YouTube videos. So imagine now demonstrating your applications over the 5G. The only application, or maybe I would paraphrase, the caveat, I haven't seen all the applications, but of all the applications, of all the demos that we saw, ours was the only one working. The reason was, it is not semantic communication yet, but the kind of encoding, of course, the specific application, specific encoding that we did, it required a very less amount of data to be transmitted to the doctor names. So that is something, even we felt for the first time. Before that, it was in slides. We were professing about it. But there, sitting in IMC where none of the devices are working, all the engineers in Delhi, they are like running around trying to make it work. And seeing your demo is the only one working, it gave us a real-world feel of the importance of such technology, particularly for critical purposes like manufacturing, healthcare, and others. So that's probably a long answer to your question, but hopefully it clarifies. Yes, please.
Yeah, so...
Okay, so can we take this
one short question,
Yeah.
See, when we are talking about multimodal AI, multimodality, this was a revelation to me that communication will be important in terms of transmitting. So semantic encoding will be important. The point I'm making is, if at all we have not thought through it, and we have to think after this possibly presentation, what do you think will be missing out when we are at a lab stage, not at an implementation stage? Will we suffer anything by not focusing on communication needs? Because communication need, we cannot do anything about it. We will depend on the communication which is provided to us by providers. So do you think we will miss out something? Or
maybe I will answer in short due to the paucity, and then we can catch up offline. So of course, there are still some of the use cases which can be done without communication, which are more of local use case. I guess the presenter before me from Meta, he was showing some of those use cases. But whenever you need to transfer that information or that experience as such, it's more of an experience, right? Over long distances, over the cellular communication, that's where we find the limitation. As long as you are the only person doing it, in IIT Madras doing an experiment, you will be fine. But when it scales, when there are tens of people doing it, at that time, we feel the limitation. And this will definitely evolve with 6G, and you are right. We are kind of dependent on the telecom evolution, the evolution of the future technologies in telecom to realize that. But again, thank you. Thank you for the wonderful questions and the very good experience and the opportunity. Thank you.
We thank Dr. Kaushik Dey for a deeply insightful session. His perspectives on XR in the 6G landscape have provided a clear vision of the future of immersive connectivity, intelligence, and autonomous systems.